Welcome to today's webinar that is dedicated to the technology demonstrators and heat pump as technologies and processes of the future. I'm Serena Scotton and I'm working at European Heat Pump Association, which is today's event organizer. Today we will present four innovative European projects, which of course are applying and deploying heat pumps in different sectors. Before starting with the project presentation, I would like to give you a short overview of today's session. As you may already know, because you attend other events in the past, this is the 5th episode of the Projects Online Talks series organized by EHPA. We will have other online seminars dedicated to heat pump applications in the upcoming weeks. So if you are interested, I would suggest you to have a look at our website and register for our upcoming events dedicated to industrial heat pumps application and digitalization in the heating and cooling sector. As well as I would like to inform you about an EHPA initiative dedicated to gathering innovative heat pump projects around Europe and beyond. This is the Heat Pump Award, which is an initiative started in 2011. And since then, we have collected more than 150 applications from 110 different cities, mostly in Europe. For 2021, of course, we will have another edition. And this year, we aim at awarding 5 categories of different heat pump projects developed at the local level. So we will award projects applied and developed on local level, projects deployed in the building sector as well as industrial. Then, of course, we will also award projects which maybe don't fit in the first 3 categories, but we find their applications very innovative. And then we will also have this year special award, a special recognition that is the most voted project among the broad audience. And this voting will be online. So if you are involved in heat pump projects deployed on local level, you can now submit your application. The procedure is online, so I suggest you to have a look. Then going back to the focus of today's meeting, I just want to share with you the agenda. So after my short presentation, we will proceed with Wim Boydens, who will provide us a presentation about the hybridGEOTABS project. Then we will have Christian Keim presenting the REWARDHeat project. Then we will go with the Heat for Cool project presented by Antonio Mingo, and we will conclude with Lynda Mitchell, who will present us the GeoAtlantic project. These are European Horizon 2020 project and Interact project. I suggest we keep all the questions for the closing 20 minutes. So what I kindly ask you to the participants is to please submit your questions via the Q&A chat. These questions will be addressed directly to me, so I kindly ask you to, every time you write your question, to please indicate the name of the speakers you want to address it. This online seminar is being recorded. The presentations and the recording will be shared within the participants tomorrow via email and will be shared on the EHPA website as well. So this is an overview of our today panel, and I would like now to start with the first presentation given by Wim.
Okay, thank you very much, Serena.
Just a second, sorry that I'm trying to share
In the meantime, good morning, everybody from my side. Did you already? No, you're still.
No, sorry.
Yeah, it's okay.
Okay, now you have the control and the floor is yours.
Yes, I'm looking to control it. I have a look. Minute, Serena, I don't see. Or can I just ask you to move the slides? Is that possible?
Yes.
Okay. So good morning, everybody. I would like to show you some demo buildings, what we have accomplished there in the frame of hybridGEOTABS project, Horizon 2020 project, at the end of the month. So we're in full work now. I'm Wim Boydens. I'm from Boydens Engineering, which is a consulting and engineering office. Also at the University of Ghent, I teach, and we are, of course, a project partner. You can move. Next slide. Serena. Serena.
Can you see? I'm moving the slides. Now I'm on the third slide with the project partners. Can you see it? Or is there
No.
No?
No, but I can go on talking. No, I don't see I don't see my slide.
Okay, maybe there is a technical problem. Let me, if you can continue maybe speaking and I'll try to fix it.
Okay,
sorry.
I'll try to catch my own presentation. You still hear me though?
Yes, and now I think you should be able to see your presentation. I think I fixed. Do you see it?
I see absolutely nothing, but then I just start talking. Okay, so the hybridGEOTABS project, you would probably see now on the screen the full description of it. The focus is really on system integration of storage, heat pump, and a hybrid in a global frame where we try to make the operation as environmental friendly as possible, as well as the design. So the early design phase, the pre-design phase. And we do this in operation by model predictive control. That's one of the important pillars of the project. Next slide, please, Serena. The project consortium, you can see them all there. It's a nice mixture of industrial companies, of universities, and of practitioners. And it was initiated by us, Boydens Engineering, together with KU Leuven and University of Ghent. University of Ghent was also appointed as project coordinator. Yes, please. Then you see they're all live people, real people coming together over the 4 years and working very fruitfully together. Next slide. Well, to explain a little bit, we'll show you a movie, and that's of course done very consciously. But I will explain a little bit the key lines, the GeoTABS concept. So GeoTABS concept is a combination of a ground source heat pump with a TAPS system. So that's thermally activated building systems that are embedded in the building structure and that try to thermally operate as emission system. Next slide. This is not new. You could say that the new wave of the GeoTABS concept started at the ending of the past century, where Bjarne Olesen from DTU, Meyerhans and partners were really putting this into practice. It did not deploy yet, really. But then later, Bjarne Olesen and Professor Helsen from Leuven University upgraded it towards better operation, better control, and better design. So this enabled a lot of buildings to be put into our landscape and that are in operation already. But in the former project, we saw some challenges. We saw that there were barriers for deployment, let's say room for improvement. Next slide. And these room for improvement were mainly on the control side and how to optimally, also cost optimally, design the whole thing. And that's why we added or we upgraded towards a hybrid to say like the limitations of the TAPS, the challenges of geothermal system, like the balance in the ground, were to be tackled by adding another system, Before, we always try to adapt the architecture, so the glazing percentage, the insulation percentage. We try to adapt that, but then we come to a building that does not respect its own architecture anymore. And let's say architecture is important. If we feel good in a building, then we are far more productive. And then the resource, being the building, is used more optimally. Next slide. So in operation, if you have a hybrid system and you have the storage, the embedded system in the building, and also the ground source, which is a seasonal storage, then it becomes quite a challenge for the control. And that's where the model predictive control really makes a difference. It's a kind of artificial intelligence. It creates a model of the building and the systems, and it uses this model to predict what will happen if certain actions are taken. And it does this time and time again, and over a long time horizon. So that means actually that the artificial intelligence or the model predictive control is choosing step by step every 15 minutes what actions to take. And as such, in operation, also the best combination of climate or environment as a target and cost as a target is achieved. Next slide. So as a summary, you see here the tabs and the geo, that's the pure system. And then added, there are other sources that are low carbon, of course, and emission systems to tackle the challenges of the tabs. And it is done by the MPC as a key enabler. Next slide. These are demo buildings, but the most of them you will see in the film that is coming up now. You can go ahead.
Okay, I'm going to share the project video.
And I'll be back after it for closing slides.
Okay, I will play it now.
hybridGEOTABS is a concept that has been developed into a Horizon 2020 project funded by the European Commission. hybridGEOTABS is a building system integrating geothermal heating and cooling with tabs, along with other energy sources, and importantly, integrating model predictive control, or MPC. Tabs are fluid-filled pipes for heating and cooling and are added in ceilings, floors and walls during construction. Heat is exchanged between building and ground via a heat pump. For all these systems to work optimally together, there needs to be a control system, which is where the MPC comes into play. The hybrid system includes secondary renewable energy sources such as solar, biomass and wind.
The MPC is needed because you have then two systems next to each other that need to collaborate in the right way. If they counteract, you're going to use more energy. In one word, it's a sustainable energy system for buildings.
We spend 90% of our time indoor, so the indoor environment is so important for our comfort and our productivity. But we have to deliver this indoor environment with as low an energy use as we can, and also trying to use renewable energy sources. And that system here is in fact doing that.
With the project, what we're aiming at is really decarbonizing the heating and cooling systems in buildings. We're trying to boost the industry and provide all the different engineers who are working in this business with some simple, straightforward tools that they can use directly at the beginning of a project.
The toolkit then allows designers to really harness all the advantages of the different components in the system already early in the design stage, because they, using the toolkit that we provide, they can anticipate the ulterior performance level of the building.
We have been working a long time on this, first by simulations of course and a virtual environment, and now this project allows to test it in real buildings, and yeah, then having the observation that it works well is of course very exciting.
5 buildings have been selected as hybridGEOTABS case studies, demonstrating the hybridGEOTABS MPC concept. They consist of a care home for the elderly, an elementary school, a multi-family apartment complex, and 2 office buildings.
We actually got this project purely out of the attractiveness of the concept. It took a lot of time to communicate with the building owner, so he understood, okay, how does this really work?
What's quite exciting about this MPC is it's a white box MPC. So in this case, we use all the information of the as-built file. So we know the exact geometry of the building, we know what is in the building, which type of insulation, which type of glazing, how much windows, how much ventilation. Looking at the weather forecast, we capture all this information into a model, and that model is then a detailed model which is able to predict what the building needs. So it's a dynamic simulation using very detailed equations. MPC is running since the end of May, and so far we are saving about 25% of energy use on the total electricity used by the building, while we actually improve the comfort.
The pottery is one of the demonstration buildings we're looking at in this hybridGEOTABS project, and it's special in the sense that up to now we have been looking mainly in office buildings, and this is an elderly care home which has other priorities, I would say.
Elderly care homes have very constant comfort expectations, and that corresponds pretty well with a hybridGEOTABS system.
With this system, when we ask heat, the system will say, okay, you want to heat now, but in half an hour you will have an internal heat gain, so don't do it. Wait a little bit and it will come just like that. So it's a very good system. It's not only cheaper, but it's also giving us more comfort. People are more pleased.
hybridGEOTABS type of system can easily be used in an all-electric solution. It can be driven completely by renewable electricity. For example, for renewables here in Ter Potterie, there's solar cells included in the roof that can be used for driving the heat pumps.
This building is the result of architectural competition, and I really appreciate not only the design of this building but also the energetical technology of this building, because of really very friendly attitude to environment and also to the life of children who are in this building.
Here the primary system is the heat pump, which produces heat and cold to the TAPS system. The secondary system here is the ventilation system. It ensures the indoor air quality.
The thermal comfort and air quality in the building is evaluated 4 times a year by conducting questionnaires with the children. Using a simple tablet application, the children are asked a variety of questions regarding their comfort levels. The results are then evaluated and the feedback used to make modifications to the controller. So far, it has indicated that the MPC, which has been running in addition to the existing system, has created more savings and better comfort.
The people took notice that something changed in the system, and especially if you compare this summer and last summer, there was quite a positive feedback from the school that the indoor environment was much more comfortable.
I must say that we are really very satisfied with this energetical management. And in first 2 years, we must solve problems, but now it's really perfect. Not only in the winter days, but also in summer.
SOLARWIND is a showcase of innovation. Besides the GeoATABS concept, the secondary systems consist of urban wind turbines, solar photovoltaics, and a biomass wood pellet boiler for hot water production. It also features a green wall facade and green roof, as well as rainwater harvesting for adiabatic cooling and toilet flushing.
Using heat pumps and geothermal energy is a good idea because we can work with a low temperature and less energy, less electricity consumption.
Data is gathered using sensors, and every 45 days the information is sent to the Technical University in Denmark. The results will be evaluated and the feedback used to create a profile of the building to inform the MPC strategy.
Why should hybrid geotabs be used? Well, for me, it's a concept which is sustainable in all aspects. It's not only about energy efficiency, using renewable energy sources, reducing greenhouse gas emissions, but also social aspects. Also ecological aspects. You have no chimney, no pollution.
The main strong point is the liberty of space. You have nothing here. This enables you to choose a layout. The biggest investments are embedded in the ground and the concrete, and they don't need any cleaning. Another issue is that you have a liberty towards the grid. If prices would be varying, you can ask the MPC to look at activating the building at the moments where the energy delivered from the electricity grid is as clean and as cheap as possible. So it combines an ecological target with a financial target, and I think that is quite unique. Okay, thank you for watching. Maybe to say that the last two slides are mainly showing information on where you can find us, showing the website, and also showing the deliverables that are available on the website. Amongst those, there are technical schemes, generic schemes. There is a tool for pre-design, early design that is elaborated that will be accessible through the website as well. We have an energy dashboard that was created during the project. So a lot of information is available for the early design phase and the operational phase. And we also just are printing a guidebook that will come out in 2 weeks. So I would say just one more thing, that the follow-up is creating a knowledge center. It will be called Enercore, trying to tackle this complexity of hybrids, of controls, and of easy, early pre-design to give a fair chance to complex system in comparison to other off-the-shelf systems. Thank you very much.
Thank you very much, Wim, for your presentation. We can proceed now with the second presentation for the REWARDHeat project. So I would like to introduce Christian.
Yes, hello, you hear me?
Yes, I can hear you. I'm sharing now the controls with you, so you will be able now to start your presentation and have the control, hopefully.
Let's see if it works. Yes.
Yes.
You see the slide moving? Yeah. I
Yes.
think I cannot move backwards, so okay.
Okay, so I did. Okay, thank you.
So also, my name is Christian Keim, or Christian Keim. I'm German. I work for EDF in Marseille, in the south of France. I introduce you today just one demo site of the bigger REWARDHeat project, which is a Horizon 2020 project, which now has 1 year, which is a very big project, and I really invite you to visit the webpage to give more information about the project, because we think we already have some minutes delay, so we try to make it really brief. Within this project, I move to the next slide if it works. Yes, so Seyne-sur-Mer is very representative for us, not because it's the most innovative network or whatever. What interests us with this demo site is that it's really meaningful for the south of France. What has to be understood in the south of France, we're not working just on heating, but also on cooling. So we need the cooling degree hours within our business model to be able to ensure the running of these networks through the entire year. And so have enough volumes of energy to deliver in order to make it a viable business model. And in this case, low temperature networks or neutral temperature networks, like you call them, are really a model to pursue for us. We have seen the last 10 years, 1 decade, the development of first projects. And today we really have just a handful of them in the south, but really focusing on that as the way to go in the region. Seyne-sur-Mer is a small, it's a town of about 65,000 people near the port area of Toulon, which might be more known. And they had invested in the early 2000s in a first network. It's a seawater-based network, which on a small scale for having a first test pilot. And then they decided to make this infrastructure part of the one of the main pillars of the energy transition strategy. And so launched in 2018 a call for tender, public call for tender for opening this network to competition and make it bigger, scale up the system, connect new customers and make it more efficient, because they were known about the limitation they had on that point, what they had installed. So the network is operated by Dalkia, so it's a subsidiary of EDF. Which has a 20 years public delegation service contract with the city for the exploitation. And I showed you the different main numbers we want to achieve with this network. So just about the network itself. So you have 3 main blocks. You have your first seawater loop. So it's how we have a pumping station, exchange station, which actually draws and injects the seawater from the port area, but at about 4 meters depth. And this ensures that, seawater is in a closed cycle and doesn't interfere with the primary network, which on the second block you see, so the low temperature loop, which is actually filled with clean water, so no problem with the corrosion of the piping, and is operated depending on the temperature of the sea, which varies about between 12 and 25 degrees during the year. And then this loop, this low temperature loop, which actually a 2 piping system, distributes the heat in the calories, let's say the water, to the building substations, which then have concentrated heat pumps to rise or lower the temperature in the building, so extracting or injecting calories from the low temperature loop. So a completely centralized system. Let's move forward. Yes, so you have the general overview of the first system as we got it a few years ago, where you had just 4 main customers. You see on the top, you see the pumping stations, which is sized to about 5 megawatts of power. And then you have the first 4 customers that were connected. And then on the right side, you have the expansion plan. which was mostly is mostly composed of 3 main islands. So we have on the west side, we have a particular one. So there we have a substation, which is actually heat-only substation, which should deserve the whole area with just heating. But this, at the moment, is on hold. So it's not realized at the moment. What is realized is the school island, extension of the school island, and on the east island, where we connected the new customers, which are delivered right now. So let's move on. What we integrated as scope into the project, because the network is existing, what we want to do is to connect the SCADA system we have. It's a WIT system, WIT. It's based on 4G technology because we have no fibers running through in the network. And this one, to enhance it with our own platform, is called DEMiX, which is a platform for smart control, first of all with forecast capacities, then optimization. And so we should be able to enhance the dispatching plan, different power to be delivered and the different system parts, and so get better running efficiencies in the network. A second point, what we integrate inside is also the question of PV storage, because in low temperature networks, which have actually equipped with these heat pumps, being able to supply the electricity via PV is really an appealing model, because today with these networks, we are about 70% of renewable share. We still have 30% which are not renewable because they are withdrawn from the grid, which in terms of CO2 content in France is not an issue because we have one of the lowest in Europe. But at the same time, we would like to achieve higher shares of renewable in the system. So being able to run the electricity needed for the heat pump with PV is a really important task for us and to tackle in this southern region for sure. And then we have another issue we would like to handle is connected with thermal storage. So we wanted to integrate storage, also thermal storage in the network, and go deeper down into the customer side. So we call it in this slide EPC++. So going further into new models, explore new models for energy performance constructing on client side, in connection with storage, in connection with other actions. So coming to the DEMiX platform, our DEMiX platform is an EDF product. And what you see here is kind of our objective. It's not where we are today. The objective is to have behind one only and one interface to have the conception part and also the exploitation operation part of your network within the same system. And really in the long run, it should be really a tool that enables the sharing of experience, models and data about the users, and really be kind of a center to centralize all this knowledge and operations. Let's move forward. Yes, so here you have just an interface of the DEMiX conduit platform. So it's the exploitation part and not go into the planning part of the system. So what you see here is just different interfaces as it runs on centralized networks today. What should be retained that, well, it's an exploitation platform for which we need day plus 24 hours. So 24-hour forecast of the loads, productions, and the possibility to optimize that in an economic manner. So be able to have the dispatching of all assets in an hourly time step. But yes, then from the forecast part, we have a tool, it's called FORECASTHEAT, also developed by EDF. And actually it's based on learning algorithm, which usually borrow from artificial intelligence mixed with other type of solutions, which give us very good results on at least on the centralized level. And now with the project, we're going down to the substation level and apply it for both heating and cooling. And we are quite confident to be able to increase the performance of the network already thanks to ameliorating the forecast capabilities of the network we don't have today. Really the core and let's say the challenge of this approach of this platform is on the part of the optimization. Today we have the system running on centralized networks where you have just one production station, and let's say the problem is fairly not simple, but well, it's solvable, which is not the case for this type of networks in which we have a lot of let's say the energy production is decentralized. And these heat pumps, they are the point is that what we want to address is that having all these distributed energy stations, we know that depending on the control in the piping of the flow of the water and its temperature, which is depending on the operation of it, the previous substations, can influence the COP of each and single heat pump. So we have a model, we have an optimization problem which has not one precise solution for each and every time step we have and situation we find us. We have to take into consideration the dynamic behavior of the network. So we are obliged to, if we want to have yet a deterministic type of approach, we are obliged to go into really detailed modeling of the network down to the individual component level, and be able to use this as, let's say, our virtual twin, a digital twin of the network, on which we can run the different optimization runs in order to be able to understand which would be the most the optimal, let's say, configuration of the network at a given time under certain conditions. So we are moving down from, let's say, a central optimization down to a decentralized problem, and that's really the action we want to tackle. Next one. So I think it's the last slide. So we are today with DEMiX Conduit. As I said, we are modeling the whole network in all these components, and we're working on the setup of the optimization framework. And we're also kind of closing now the definition of the overall structure of the whole ICT system and operation of the system. And we should start demonstrating to go live with this system in October this year. The PV system and battery energy storage system has at the moment been stopped. We're trying to maybe move it to another network, but well, it gives important feedback of the project life, in which we were confident that we get this action done, because we had all systems, everything, all preconditions were in place to be able to make this demonstration, but we finally got no go from the client side because of insurance problem with the PV system. So let's say real life always learns us new lessons and teaches new lessons. So we're trying to move it maybe to another network and try to be able to test it anyway within the framework of the project. From the storage, there also we had some lessons from real life where we are not able to find public ground or private ground for the installation of 50 cubic meter storage system. One side because it wasn't integrated in the land use. Also, it might be underground, that would neither be possible, and upper ground, it was a lot of concern concerning the urban integration of the storage. So we have totally blocked, but we still want and we still need some storage capacities to offset some peak demands. So what we're going right now, the direction is to use the network itself as a storage. And so be able, with the advanced control we will develop, be able to go one step further and be able to operate the network to store some energy in short-term energy storage for the network. And also the energy performance contracting, we also have already signed a contract for that. And what is interesting there is the energy performance contracting. We put some tariffication to the client, which valorizes the fact that by operating his installation, his substation, which is equipped with thermal frigo pumps, so they can produce either heating and cooling at the same time. And it's a really important tool for us to control the temperature of the network. So we give him some retribution for the energy he's be able to give to the network, which can balance and ameliorate the overall COP of the cascade of heat pumps behind. So well, I think that's all from my side. Yes. So please don't hesitate to put questions afterwards in the Q&A session. Thank you.
Thank you very much, Christian, for your presentation. Thank you. I will now remove the control. We can go now with the third presentation. We can proceed with the Heat for Cool presentation provided by Antonio. Antonio, I'm going to share the control with you.
Thank you, Serena. Could you hear me properly?
Yes, the floor is yours, Antonio.
Okay, I will check configuration. Okay, it looks to work. Okay, my name is Antonio Mingo, and I am the person responsible for the Valencia pilot site involved in the Heat for Cool project. Here in this slide, you can check some of the partners involved in that project. And Valencia is not the only site. There are 4 different sites. 4 different sites in Budapest, Sofia, Poland, Chorzów, and also in Valencia, Spain. Fit for Cool project is a project still live. It is still running. It shall be finished for ending last year. But because of COVID, it was necessary a short extension to complete some of the tasks. The project proposed innovation, efficiency, and cost-effective heating and cooling solution to optimize the integration of 6 technologies. Not all the sites include all the technologies. No? The technologies for the project are absorption heat pump, PCM, storage batteries, AC beams, solar PV, solar thermal, heat recovery from sewage water. In case of Valencia, probably maybe the one of the cores of the project. We are especially focused about the absorption chiller. Here you can see the building. The building is a 4-floor with 12 apartments house. All the systems are installed in the roof. This is a scan of the schedule or summary of the monitoring and control system with the main screen. Finally, I decided that probably it will be easier if I try to explain the installation with a very domestic video. It's not a very good production, but I think that it will help all of us to realize about how is installation. I would like to remark that there were a previous installation when some of the new equipment were installed. No? That is what we are going to see for the next. Oh, sorry. Serena, could you please play video? It just will be for 5 minutes.
Yes, I'm going to share the video now. Okay, share video. Okay, I will play now.
Thank you.
Estamos en el edificio piloto de Valencia, donde se ha montado la instalación de calor-frío sobre una instalación previa existente, ¿no? Y ahora vamos a explicar cómo se ha implementado dicha instalación sobre los equipos que se disponían y ya se disponían y estaban operativos. Fundamentalmente se trata de 3 bombas aire-agua que suministran de agua caliente y fría a inicialmente 2 depósitos, uno de frío y otro de calor. Lo que se ha implementado ha sido una bomba de absorción que está dentro de esta caseta. Aquí la veis. Este es un cuadro de control. Se ha implementado también una cubierta solar térmica Decíamos que la bomba de absorción va a generar agua fría a partir de esa agua caliente disponible. Y esa agua caliente bien proviene de las 3 bombas de aire-agua que ya existían y que hemos mostrado, o bien proceden de esta nueva instalación solar térmica, que está en la cubierta. Ahí la tenemos. Este es el campo solar, donde se ubican los colectores solares térmicos de placa plana. Ahí fondo, si os fijáis, vemos el sensor de radiación y nanómetro. Como decíamos, la instalación ya contará con un tanque de calor, que es este, un tanque de frío, que es este, y se ha implementado otro tanque de calor más que está conectado en serie con el ya existente. Los 2 tanques de calor bien suministran agua caliente al sistema central, donde en cada planta tenemos un intercambiador de calor para el agua caliente doméstica y una serie de fan coils en los apartamentos, donde se transforma esa energía caliente o fría del agua en calor o enfriamiento, refrigeración, para ambientar el apartamento. El agua caliente, que bien proviene de la cubierta que hemos visto o de las bombas existentes, se pasa a la bomba de absorción, que es este equipo, y genera agua fría que se incorpora al depósito frío para circular a cada planta. Todo el sistema está controlado por un cuadro eléctrico, que es este que os muestro. A la derecha hay una pequeña caja estanca donde se ubica el router, y luego hay dispositivos auxiliares, por ejemplo, este calentador del agua del circuito de refrigeración, para que no se congele en invierno y estropee el circuito. Y luego pues, la bomba de absorción cuenta con ventilación forzada y un rudimentario sistema de calefacción, porque aquí es rarísimo que baje de los 0 grados la temperatura ambiental. Tenemos también un sensor de temperatura y humedad, un sistema de decantación magnética para evitar óxidos en el circuito y un sistema de descalcificación. Esto aquí las aguas son bastante calizas. Todo el sistema se encuentra monitorizado y controlado por una aplicación informática en la que aquí se muestra el esquema técnico y donde están reflejados todos los puntos de control y medición que dan lugar a las series de datos que luego se utilizan.
Vale, como podemos ver, por un
Okay, Serena, if you want, we could cut heat now to avoid to extend too much, okay? Anyway, if you want to share that video with anyone interested about it, there is no problem. Rest of the video we explain the installation for each apartment and controlling system and so on. Okay, thank you. Okay, as you check it, the core of the installation is the absorption pump. What is an absorption pump? Well, an absorption pump basically is a chiller powered by hot water. We produce hot water through the collector system, solar collector system, and we feed with this hot water
the chiller through a process of absorption. The absorption is able to cooling the cold water tank up to 8 degrees or something like this. Later, that cold water will be used for cooling system for the different apartments using a fan coil. As I said, this project is not still finished, but I will try to get some conclusions of the operation of the system during last year. The first and probably the most important one is the absorption chiller is able, under proper condition, to operate, providing a very good COP values. Efficiency is quite close to the technically estimated one by the manufacturer, who is Fahrenheit. It is close to 0.5. Here we can see some figures with different recooling temperatures, but they used to convert in that value. Well, I will have to say that this result is absolutely critical for the proper operation of the system. To install it inside a room for a case, sizing correctly the support cooler system. What I mean is that the worst experience that we have during the operation of the absorption pump was that with temperatures over 30, 32 degrees, efficiency decreases significantly. Even that with temperatures over 30, 34 degrees, cooling production was minimal. So that is the reason, because it's so important to install in a proper condition inside a room or inside a case. Anyway, this equipment is not an outdoor equipment. Regarding some more technical difficulty problems that we have during the operation, we were really getting crazy about the interferences with the rest of the system, especially with the three-wave valves that connected the heat water circuit with the cold water circuit. It was really properly fit to avoid pouring hot water into the cold water circuit, because it is absolutely critical. Regarding the solar system, not too much to say. It's a very quite well-tested technology. We installed around 20 solar flat collectors with a total surface of 50 square meters. And in a place like Valencia, when solar radiation is quite high during a long year, the result was that most of half of the total hot energy requests for domestic hot water and heating a long year were covered by solar production. And regarding replication, what we did was simulating building, simulating energy structure, system structure, and running it for different sites with different solar radiation conditions, with different summer and winter conditions. And the conclusion that we get are quite similar that we expected. So in places like Valencia or the north of Spain with very hot summers, and with very high solar radiation on a long year. The energy saving that we could get is around 30, even 35% of energy. It perfectly fits with the target of the project, and it also fits with the premise of a 10 years payback that we estimated at the beginning of the project. Okay, I didn't understand too much about it, but I hope you have any question that we will have to answer. And anyway, here you have my email in the last slide. If you can ask me for anything regarding any technical detail or so on. Okay, thank you very much.
Thank you, Antonio, for your presentation. We can now proceed with the last presentation for today. Lynda, who will present us the GeoAtlantic project.
Hello, everyone.
The floor is yours, Lynda.
Thank you. Hello, I'm Lynda Mitchell, the manager at ALIenergy. It's a regional energy agency based in Oban on the west coast of Scotland. ALIenergy is a charitable organisation working on fuel poverty, energy education and local renewable energy projects. And we're delighted to be a partner in the GeoAtlantic project, working alongside partners from the UK, Spain, Portugal, France and Ireland, coordinated by the Council of Orense in Spain. The GeoAtlantic project aims to encourage the transition away from dependence on fossil fuels for heating by promoting the use of renewable heat from the ground. In this talk, I will focus mainly on our demonstrator project, a Scottish demonstrator project, the feasibility and design of ground source or water source heat pump systems for use in buildings owned by Scottish canals, many of which are situated adjacent to the canal waterways. Nothing has yet been installed on this project, and my talk focuses mainly on the early stage difficulties associated with such a project during initiation, procurement, feasibility, and associated with renovation and retrofit. This was actually our third attempt at a demonstrator project after two others stopped at an early stage due to issues with the co-financing. Now, can I move on to the next slide? Oh, thank you. Scottish Canals is a public body responsible to the Scottish Government for the management and development of the Scottish Canals waterways and surrounding estate. They own several hundred buildings beside the canals, and this slide just shows a selection. By using these assets wisely, Scottish Canals' intention is to enhance the future quality of life for Scotland's inhabitants and to create a more successful, sustainable country. Because most of the buildings are right beside the water, we were looking in particular for opportunities to install water source heat pump systems. So, early in 2020, we started the procurement process for a technical subcontractor to work on the feasibility study, to consider the whole portfolio of buildings and select those most suitable. But unfortunately, the virus pandemic interrupted the process and caused a delay of several months. We then had to rewrite the invitation to tender in the light of the virus-related restrictions and change it to a much more restricted desk-based exercise, although in the event, a few site visits were possible. The tender was won by Turner Services, and we created a team consisting of the environment manager at Scottish Canals, Olivier Lassiere, along with consultants Mark Henderson, Agris Bermanis, and Keith Kensley from Turner Services, and myself. And The next slide, please. Sorry, I can't seem to change it myself. Thank you. Across the Scottish Canals estate, there are 278 documented buildings in total. The process used for shortlisting is summarised here. It was quick to rule out many of them on the basis of small size, dereliction, lack of heat demand, or even lack of electricity connection, ones let or leased to other parties, or designated as low priority for various reasons by Scottish Canal, and also ones situated out with the GeoAtlantic funded study area in the west of Scotland. This left a short list of 19 buildings of particular interest for more detailed consideration to understand usage patterns and heating profiles, fabric condition, the nature of the site and proximity to the canal, and the existing heating system type, age, and condition. A number of these were then ruled out for reasons including older buildings with very poor insulation, where significant refurbishment to reduce the heat loss would have been required, and buildings which only required partial heating, where the heated part was deemed too small. We then focused in on the top 10 buildings or clusters of buildings, all of which could potentially be suitable for a ground or water source heat pump system. The buildings were investigated and ranked in terms of the financial case and also in terms of the carbon emission reductions. So let's take a brief look at some of these in more detail. Next slide, please. This is Clachnahari Sealock facility. It's a multi-use building cluster, currently heated with a combination of electric storage heaters and oil. Water and ground source heat pumps are options. Water with an open loop system, taking water from the canal upstream of the lock, or ground source using boreholes. Both are doable, although initially more costly when compared to an air source system. However, you can see from the figures that the payback period is quicker for water source, as long as the RHI, the UK's renewable heat incentive, is able to be claimed. Reducing heat loss from the building would be important prior to installing any low temperature heating system. Next slide, please. Seaport Marina consists of offices, customer facilities, store and plant, and is currently heated with a mixture of electric storage and panel heating, with quite high energy costs. A water source heat pump is an option with either an open loop or closed loop system. But again, the figures show that although an air source system would be cheaper to install, the payback is quicker with water source, as long as the RHI is able to be claimed. Next, please. Dochgarach Maintenance Depot is a general maintenance workshop for storage and trade with drying area, welfare and office facilities. It's a steel-framed brick building with part metal cladding, refurbished in 2005 with double glazing, electric heating and hot water. A water source heat pump is an option here, with either an open loop or closed loop system, but the pipework would need to cross a road. A ground source heat pump would avoid the need to cross the road, drilling boreholes instead in the yard. Equally, an air source heat pump system could be installed, and in this case is shown to be the much cheaper option. Next slide, please. The Caledonian Canal Centre is a tourist destination, cafe, takeaway, kitchen, office space, commercial retail outlet, ensuite rooms, and housekeeping. It had a major refurbishment in 2018. The heating is currently all electric via panel heaters, and hot water is provided by an LPG boiler. Unfortunately, this site is very tight, again with a road between the building and the canal. And also, there's a lock at this point of the canal, which would add a level of complexity that would unfortunately make a water source option both challenging and expensive. The tight nature of the site would also make it difficult for ground source. An air source heat pump would be significantly cheaper here. Next slide, please. The Gaelochy customer facility, constructed in 2007, is an electrically heated building with toilet, showers, storage, laundry and plant. An IBM Terra heat water source heat pump was installed, but was later decommissioned because it didn't meet the shower and laundry requirement. It's worth investigating whether the heat pump could be replaced with a more modern and therefore efficient model that would achieve the temperature and hot water demands. This would require a site visit to try to ascertain whether the water source collector system is usable and correctly sized, such that it would service a new heat pump. Meanwhile, a calculation based on full system replacement, if that were necessary, shows that an air source system would be cheaper. And next slide, please. The Crinan Canal headquarters old building. The Crinan Canal headquarters has in fact now moved, leaving this building currently unoccupied and due to renovation. The ground floor is currently heated by a 5-year-old oil boiler, and upstairs there are electric storage heaters. This planned renovation is an excellent opportunity to incorporate renewable heat. Improved insulation and airtightness will create a building suitable for a low temperature heating system. Oversized radiators can be specified to maximize system efficiency. Allowance can also be made for a plant room to house a heat pump and hot water tank. Ground source is an option for this building. There's limited available land for a ground source collector system, but plenty of space for drilling boreholes. However, air source would still be cheaper. And next slide, please. The boathouse at Ochenstarry. This building has an existing old and dysfunctional water source heat pump, which has been decommissioned and a gas boiler installed. The recommendation here is to replace the heat pump system with a new water source heat pump, because the cost of system fault finding, repair, and possible recommissioning would be significant, with no guarantee of reinstating a resilient system that remains operational. The installed system is around 15 years old, and heat pump technology has improved significantly during this time. And also because installing a new system with guarantees within the RHI qualifying timescale means that it could qualify for RHI payments for the next 20 years. The existing wet heating system with radiators seems to be in good order and is already sized for a low temperature heating system. The existing gas boiler can be retained as a backup. The figures show that although a water source system would be a little more expensive than an air source system to install, the payback period, if RHI is claimed, is significantly faster. A ground source heat pump with boreholes is also an option at this site, although expensive. Next slide, please. And finally, the Scottish Canals head office building, their largest building at over 1,000 square metres, including a connected extension. Currently heated by a gas boiler, which is at least 15 years old, with additional heating and cooling delivered via multiple air-to-air heat pumps and convector fan units. The recommendation here is for an open-loop water source heat pump with the existing gas boiler retained as a backup, and upsizing of radiators to ensure the best system efficiency associated with a low temperature heat pump system. Next slide, please. The summary tables show the top 10 buildings and clusters of buildings ranked 1 to 10 in economic terms and also in terms of carbon reduction. The calculations used in these tables take into account income from the RHI, the UK's Renewable Heat Incentive, but if you take that away, it doesn't really affect the order of ranking, it just makes all the paybacks a little bit longer. Next slide, please. With no RHI. Although it may be feasible to install water source or ground source heat pump systems in each of these buildings, it's interesting to note that in some cases it's significantly cheaper to install air source heat pumps. This is due mostly to the lower initial capital cost of installation. This is an interesting finding which may of course explain one of the reasons why water and ground source heat pumps are not more common than they are. However, in several cases, a water source heat pump was shown to be economically the best option, and also in several more of these buildings, the water source heat pump option, although initially a bit more expensive in terms of capital outlay, gave a payback period that was still faster than the air source heat pump option. And the last slide, please. The total annual carbon emission reduction, if all of these top 10 buildings had heat pumps installed, would amount to 102 tonnes of carbon dioxide saved, which is over 10% of Scottish Canal's total emissions. The project has shown the potential for water and ground source heat pumps and other alternatives across the Scottish Canals estate, and also highlighted the importance of a fabric-first approach to energy efficiency and carbon footprint reductions. And thank you very much. If anyone has any questions, please ask in the Q&A session.
Thank you very much, Lynda. So as you can see, all the speakers have shared with us their presentations and their emails. Now we can officially start the Q&A, but if you want to personally engage, you can send an email to the speakers and they are more than welcome to answer to all your questions. So let's start with the Q&A. I'm checking now the questions we received. I would like to address this first question to the entire panel. So how the COVID pandemic affect the work you were doing on your demo sites, and how did you react? So Lynda, if you want to be the first one to answer.
It had a very serious effect, really, because the restrictions that were imposed upon us were quite severe, but also because they kept changing. So it was very difficult to plan anything. It meant that a lot of site visits had to be cancelled. It meant that our contractors were unable to go to the buildings that they should have gone to. And a lot of the work had to be done as a desk-based exercise, which was really quite a compromise.
Okay, thank you for your answer. Wim, would you like to provide your answer?
We had, next to the technical approach, we had a lot of questionnaires and surveys in the demo buildings. And of course, except for the elderly care home, the office buildings and the school were almost without any occupation. But it seemed that the model predictive control dealt very well with it. It actually captures the CO2 emissions, I mean the emissions indoors, and it knows the indoor environmental quality, and it reacts by managing and controlling the installation in the appropriate way. So you could actually say it adapts to different situations and it reorients. So it was not disruptive, but of course for the research institutions and then mainly the DTU from Denmark, of course they, and Maastricht also, they did lack some information on do the occupants consider the indoor environmental quality better or less. So that was. Did you hear me or was I muted?
Okay, no, I lost you for 20 seconds.
Okay, so on the technical side, everything went well. The questionnaires, of course, were not as abundant as before. That's a little bit of pity.
Okay. Thank you for your answer, Wim. Christian, would you like to provide your input?
Well, some few additions to what has been said, indeed. I mean, from an operational point of view, for delivery of the network, we had to accumulate a few months of delay for the delivery of the substation, technically speaking, because of the stop of the works. Similar, we also have the problem that we have office and educational buildings which are not occupied during certain parts. So we will have some bias in the data we will have, but there again, forecast system optimization, they are adaptive, so they should have no problem, let's say, with that part. We're also confident that won't impact things. And well, and then from the commercialization side, I would say the COVID has maybe postponed some decision, and real in the client side they have other priorities, and so contracts that were under discussion were much more difficult to achieve. and some were just stopped, and we postponed discussions once, let's say, priorities are resettled and things comes back to normal.
Thank you. Antonio, would you like to provide your perspective for the Heat for Cool project on this?
Yes, of course, it's a quite interesting question. It was a real problem from the beginning, even up to now. From the beginning, because even though the installation was almost finished, there were some details that we had to attend and we had to fit. And during a long time, close to 3 months, it was impossible to access to the building because of the restrictions. Even nowadays, there are restrictions, and it is quite difficult to access to Valencia city. Yes, and please consider, even if I didn't mention it, that building is in the downtown of Valencia, so it is very quite well affected area by COVID. I think what's even worse for the situation. During restriction period, each time that we had a problem, as for example, I remember that we had a problem with one of the electric pumps, and there were a long delay to be able to attend to repair it, because there were no people willing to, no company willing to go. On the second side of the problem, I would like to mention that we expected a total occupancy of building during the whole period, during the whole testing period, but it was not true. Because of restriction, occupancy was low during a long period. Even during restriction, it was minimal. During March, April, May, it was minimal. Later, it was 70%, 60-70%. Some weeks maximal completed, but not all the time it was what we expected. As you can imagine, with a system that depends on the demand, because you have to keep system working independently of demand. It has a really important influence about the operation of the system.
Yes, thank you, all of you, for your contributions. Wim, I see that you raised your hand. Do you have anything to add?
I did, Serena, because I forgot to mention a strength of the system in the COVID period, especially in the elderly care homes, because all the older people, they had to stay in their rooms. And the choice for a system with taps, it really provides a comfort in all the rooms without a big investment of an emission system per room, because the slabs are all cooled. So it means like that did go well in the COVID because there were no people that were infected that had to stay in a hot room in the summer period. So the comfort did help there to be ill, actually. And I hope everybody survived, but they did in the elderly home that we had as a demo building.
Good. Wim, since your microphone is still on, I have another question for you. So what are the next steps and the next process ahead in your hybridGEOTABS project?
Well, what we did is the MPC, so the model predictive control, was elaborated far further. There was also a tool chain to develop the control system less, how do you say, with less burden for engineers. So to do it more quickly, semi-automated. And we also developed a tool to have a good feasibility study and a pre-design study in a very early stage of the project, where we can really compare it to more, let's say, fossil or conventional systems. Those two elements, they have further work. We can enlarge them towards other systems. We can assess also the advantages towards the grid of the all-electric heat pump-based buildings. And that will be done in the knowledge center that we will call INERCOR, where we try to keep the close bonds between research and industry, manufacturers, and consultants and practitioners, even architects. So that is something that we're putting up now. Okay, these are hard times to put something up with networking, but to try to get all the important players that want to move forward in this knowledge center. So if any questions about that, how we proceed, you can always send me a mail and ask me what the evolution is.
Yes, thank you very much indeed. Yeah, remind to all the attendees that you can still use the Q&A chat. We still have a few minutes of online seminar. Otherwise, you can directly contact the speakers. Now, I would like to address questions, less clarification to Christian, because I noticed that in your presentation, you mentioned that the system, there isn't an overall optimum, and I would like to ask you if you could clarify it or maybe better explain it. Thank you.
Indeed. The point is, if you take a traditional system, you have one production station, one energy station, which produces the energy for the whole network, and customers are just equipped with a little bit of pumping and exchangers on the client side. So indeed, you just have to, your optimum is located at the energy station, and you get it more or less by metering your in and outlet piping from the central station. Whereas in this system, all your customer actually, your production is dislocated on the substation side, on the building side of the customers. So you have a lot of energy producing station, and each and every one is equipped with a heat pump. Might be just heating only, might be heating and cooling, or possibly to either produce heating or cooling. And in this case, your COP of your heat pump will not just depend on your set temperature on the customer side, but also on the temperature of the network, or the primary network, and on the flow rate it has. So if it would be completely, let's say, deterministic, it would be perfect. We could maybe say we could find an optimum for each and every substation. But the problem is, as we have changes in the water temperature, depending on how a substation has been operated. So take the example in which you have a few which run on heating and a few which will have provide cooling. Some will extract calories and some will inject calories in the system. And so if we now produce cooling, we just need heating, let's say, for customer number 2, but we are producing cooling with customer number 1. He will influence the temperature on the network for customer number 2 and influence his COP, because we have operated substation number 1 under this and that condition. So indeed, we don't have one optimum for all the substations. We have an optimum for each and every substation, but which might not correspond to an optimum for the whole network. So what we have a convergence of parameters, which will give us, let's say, an optimum for the system, but which will always be related to his historic, let's say, his past operation and the current condition he's in, than what we foresee for afterwards. So we're totally obliged to run the system, a digital twin of the system and optimization problem in parallel, to see which are the best parameters we can converge on, because they won't never be perfect for each and every substation. I don't know if that makes sense.
Yes, yes. Thank you very much for your comments on it. Now I would like to proceed with what I think will be the last question for today. And I would like to address it to Lynda, because during your presentation, you mentioned the UK Renewable Heat Incentive. And I would like to ask you if you could maybe tell us a bit more how it works and if it is still available.
Sure. The Renewable Heat Incentive is a UK government environmental programme that provides financial incentive to increase the uptake of renewable heat. It's been running for at least about the last 10 years, and it provides various different tariffs per kilowatt hour for different technologies and different sizes of installation. And eligible non-domestic installations then receive quarterly payments over 20 years based on the amount of heat they generate. The scheme was due to come to a close soon, but however, because of COVID-19, the UK government has announced an extension, a one-year extension, to allow applicants to complete their installations, because so many businesses are having to deal with not only COVID-19 issues, but also Brexit preparations and Brexit-related problems. And because heat is one of the UK's biggest hurdles on our road to net zero. So for the extended timetable, applicants need to demonstrate that work has already started on the project. Work was already undertaken prior to August 2020. And then there's also an intention to replace the RHI after it finishes with a new clean heat grant that will aim to help both households and businesses decarbonise through technology and help us all to move towards our net zero target.
Thank you very much, Lynda, also for your clarification. I see that we don't have any new questions here in the chat, but I would like to answer to some points that were asked before. And I take this opportunity to remind to all the attendees that tomorrow you will receive via email both the recording of this online conference with as well the presentations provided by our speaker. I would like now to thank again the panel for being here today and provided us this very interesting presentation about these European projects. I thank also the attendees for joining us, and yeah, I wish you to have a nice day, and tomorrow you will receive all the material. Thank you very much.